This is Chapter 16, Section 2. We've just finished up talking about enthalpy, so in today's lesson we'll talk about enthalpy, entropy, Gibbs free energy, and at the end of all that I will do a synopsis of notes as far as putting all of them together so that you can see the ins and outs of each of them within one slide. So as we get started, I will try to go over the important parts of each slide so you don't have to write down every word. So as it says here, the majority of chemical reactions are exothermic. We do have some endothermic reactions that occur spontaneously, which is not common, but let's go look at something else. If we are looking at entropy and reaction tendency, entropy, we're going to use change in entropy as a delta S. They're using the example of melting as a naturally occurring endothermic process. So an ice cube melts spontaneously at room temperature. You have well-ordered arrangement of water molecules that become less ordered liquid phase molecules, and the system goes from one state to another without an enthalpy change, and it does so, though, with an increase in entropy. So the process of melting, we do go from one state to another without an enthalpy change, but there is an increase in entropy. In this example, we have the decomposition of ammonium nitrate, and it has already been balanced for you. We're going to look at the coefficients out front. So the wording down at the bottom, you can see we have 2 moles of our reactant, but those 2 moles quickly turn into 2 moles of product plus 4 moles of product plus 1 more mole of product right there. And if you look at the arrangement, your right-hand side is definitely more random than what's on the left side. So the right-hand side has a higher entropy because there's more chaos than what the reactants is that you started with. So the tendency in nature is going to be to go in the direction. Sorry about that. Tendency is to go into the direction that increases the randomness of a system. And the word entropy, if you were to define it, is defined as a way to measure the degree of randomness of particles, such as molecules within your system. So entropy is a measure of randomness. Also, as we look at entropy, if we were to look at an equation a lot like we did with enthalpy, your change in entropy would be entropy of your products minus entropy of your reactants. As I see the different delta S values that are here for different reactions, I'm going to show you a little bit different way to look at each of these. In the first two, if I look at how many moles that we have over here on the reactant side, so I see 3 here and 1 there, but in this top one, the number of moles produced on the product side is 1 plus 1 plus 3, that's 5. And in the second one, it'll be 1 plus 1 is 2. So in both of these cases, the forward reaction is going to be favored. And you can see by the delta S values being positive, the forward reaction is favored. In the next 2 examples, though, I have 2 reactant molecules or moles that are producing 2 moles, and in the fourth one, 1, 2, 3, creating 1 plus 2 is 3. So again, 3 moles to 3 moles. These 2 values right here are really close to an entropy change of 0. So forward or reverse is neither one is technically favored. And in our last example that we have, 2 moles plus 1, that's 3 moles, and 2 for the last one, going over to 2 moles and 1 mole. In both of these, you can see that we have larger negative values for entropy. So the reverse reaction, if I can spell reverse, the reverse reaction is going to be favored in those last 2. So just some quick notes on entropy and trying to understand it. If you look at the different phases that you have, in a solid, the particles are considered fixed, so not a lot of moving around at all. In a liquid, the system is going to be a little bit more random, so its entropy is going to be higher. And if you were to go look at a gas, particles in a gas, much more moving around. With your gas particles, they're going to be moving rapidly farther apart, and the system is much more random than even in the liquid system, so the entropy will be even higher. In this video right here, which I'm not showing, the main part of it was if you stir a system, such as stirring liquids, you will increase the entropy. If I look at the units for entropy, we've got kilojoules per mole Kelvin, and it can be found, I gave you this earlier, the difference between the entropy of the products and the reactants, so entropy products minus entropy of the reactants. If you have a positive delta S entropy, there's an increase in entropy. If you have a negative delta S, there has been a decrease in entropy. So in nature, we've got two driving forces. It wants to go towards the least enthalpy and largest entropy. And a way to predict what is going to go on here, we will look at enthalpy and entropy factored at a given temperature and pressure. And to do that, we study something called Gibbs free energy, or just free energy. It is denoted with a capital G. So when we get into these and we look at delta G here, this is going to be for Gibbs free energy. And it will combine your enthalpy and entropy functions. On the next slide, we'll give you an equation. So again, this is at constant pressure and temperature. But delta G of the system is defined as change in enthalpy minus temperature times change in entropy. And temperature will be measured on the Kelvin temperature scale. You're going to want to make sure you get this equation into your notes. Please write this chart in your notes too. It's going to give you your different values for delta S, delta H, delta G, and then tell you if the reaction is spontaneous or not. So just going through this, negative delta H and delta G with a positive delta S, it is spontaneous at all temperatures. If enthalpy and entropy are negative, delta G either way, it'll be spontaneous only if your temperature is less than delta H divided by delta S. If both delta H and S are positive and delta G goes either way, it'll be spontaneous only if temperatures are higher than enthalpy divided by entropy. And then in the last one, enthalpy positive, entropy negative, positive Gibbs free energy, it will never be spontaneous. So again, this is one of those things you would write down in your notes, and you would take the time here in just a little bit to study that and make a little bit more sense of it. If I were to show you this video, it's going to compare enthalpy and entropy. This was one of the phase diagrams we looked at. This would be for water, so temperature is over there on the y-axis and time on the x-axis. We had labeled your solid, liquid, and gas phases on here. And even these two parts right here, heat of fusion is going on when you have your phase change from solid to liquid. And then heat of vaporization is going on when you're going from a liquid to a gas. If I were to relate that to your enthalpy and your entropy, with your enthalpy, you do have an endothermic process going on as you move to the right. So we are absorbing energy to change into the different phases. And for entropy, you do have an increase in entropy as you move on, because again, between solid to liquid to gas, your molecules move around much more, create more randomness. So it would also involve enthalpy and entropy changes that are going on in your phase diagram. So please write down this in your notes. It's going to be an example that we go through. This is already a balanced reaction. Ammonium chloride that breaks down into ammonia and hydrochloric acid in the gas phase. It gives you the temperature in Kelvin that it happens at. It gives you the enthalpy change of 176 and the entropy change of 0.285. And it wants us to calculate Gibbs free energy. Tell whether the reaction is going to be spontaneous in the forward direction at that given temperature. So we have our equation, and again we're solving for Gibbs free energy. I'm not going to throw in all of the units. I want you to throw in the units though, so that you can see what units will cancel or be left over in the end. But for delta H, it is a positive 176. Temperature in Kelvin, 298.15 times delta S, which is 0.285. In those last two, the T and delta S, Kelvin will cancel. So you'll be left with kilojoules per mole, which is also your enthalpy units too. So you will be left with kilojoules per mole in your final answer. When you do your calculations for this, 176 minus 84.9, you get 91 kilojoules per mole. So to determine if it's going to be spontaneous in the forward direction, with what we know right now, and you had a chart, we have delta H and delta S are both positive. Delta G could be positive or negative, and the only way the reaction went to spontaneous was if your temperature was greater than the value for delta H over delta S. And in this case, T was not greater than that, so this will not be a spontaneous reaction. So let's wrap up a couple of things that we've learned in this section and just a little bit from the previous chapter, previous section. We talked about Q equals MC sub P delta T. So we were looking at the specific heat capacity. If Q is negative versus Q being positive, heat in. If Q is negative, heat is going out if Q is positive. And then we looked at our enthalpy, entropy, and our free energy. So description for those, our enthalpy, which is Hess's law, is an equation of state based on heat. So we are talking about heat transfer. We have delta H of the reaction is enthalpy of your products minus enthalpy of your reactants. I'm going to put a star there. We'll say what that star is for here in a minute. And if you are talking about an exothermic reaction, enthalpy is negative. An endothermic reaction, enthalpy is positive. We didn't talk about isothermic reactions, but if it was, then enthalpy would be equal to 0. Entropy does depend on the physical states. Can't write the word physical. On the physical states of your reactants and your products. Therefore, gases will have an increased entropy and solids will have a decreased entropy. Our reaction for this change in entropy is also entropy of your products minus entropy of your reactants. If your entropy is of positive value, this is going to be an irreversible reaction. And if entropy is going to be 0, it is a reversible reaction. And then Gibbs free energy is all about spontaneity. Is it spontaneous or not? And we have the table to look at that goes with that. So again, you have the table that you've got down. Again, change in Gibbs free energy can be the products minus the reactants. And for this one, your reaction happens spontaneously if free energy is negative. It does not happen spontaneously if it is positive. and you are considered to be in equilibrium if free energy is equal to 0. Now the star that we have out beside all of these, it's because those particular equations are going to use your coefficients to account for all of the moles in your calculations. So make sure you have a balanced chemical reaction, and again the coefficients will account for the moles in your calculations. So those will have to be added too.